Microphone is on. Who is holding the microphone?
You're
Welcome.
pretty good.
My voice is gonna crack. Easy. But on my count.
Wait, are we saying?
No, I'm kidding.
Let's go. Okay.
Hello, everybody. It's time. Wait, I need to Ready? Okay, I'm ready. And we have a volunteer to lead us on our initial class stretch. Ready? Take it away.
Welcome, EECS16A!
Woo! Very good. Thank you. I will need a Mickey substitute today. If anybody wants to volunteer, let me know. Because, you know, when I tell you, I give you my best advice to you and I say, don't skip class to do something else. Because if you skip class, then, you know, you will have more work to do later. Guess what? Mickey is catching up with homework. He has a big deadline tomorrow, so I told him, why don't you take that time to finish up? So you're going to be my Mickey? Okay, what's your name?
Div.
Oh, Div again.
Yeah.
Oh, Div, now I see you from close.
Yeah.
Well,
I got a haircut.
I really appreciate, yeah, you did have your hair. I really appreciate your help. You are very good Mickey. Okay, we have Div. Div with the microphone, me with the questions, and you guys with the answers. Let's do it. Okay, last class, we started a very nice concept of equivalence. And why is equivalence important? Equivalence is important because when you have, you can simplify your circuit analysis by saying this block of elements behaves as similar or equivalently to this block that's much simpler. So if you have a way of simplifying your circuit analysis, then it's a good tool to have. If you were working on the coding part to do simulations for your circuit, then it means that your code will be simpler, less room for mistakes. And when you're trying to debug in the lab and understand how the circuit works, it's also good to have a way of simplifying, right? So that was equivalence. And we are going to be playing with this concept the entire class today also. And from now on, I'm going to be talking about equivalence all the time. Then I showed you this circuit here, where we use this as an example for equivalence, where I said, okay, if we take this simple circuit, which we have worked with before, which was only a voltage source and a resistor, and I said, okay, we can do the analysis of this circuit, and then with this analysis, by saying, just by calling, the back mic, so far it shouldn't be picking up. Okay, can you leave it off while I'm talking just in case? But I don't think it is, it's probably up there, but I don't see Adam up there. Okay, I put it a little bit lower. So, I said, if we label here a current for this I element, and the element that I was calling here was the circuit, which I said, okay, it's unknown, let's say, we pretend we don't know what's in there. Then we did an analysis where we could plot this line to represent the current voltage characteristics for this circuit, the IV curve. And then we said when the current is equal to 0, if we say current equals to 0, we get this point here on the plot, which we called Vs. We also showed the equations that we could also get these values. When the current is 0 here, then we get that the point that we are plotting is Vs. And then we said, okay, when the voltage is equal to 0, we get the intercept here on the vertical curve, which is given here by minus Vs over R. And we know from these curves that the slope is the inverse of the resistance in your circuit. And this is very nice because, okay, we are looking at only one resistor. Today we are going to put more resistors in the equation here. And then I gave you the Thevenin and the Norton equivalent as an example with a certain methodology. And what was this methodology for? Let's see. Let's say I give you a box that has circuitry on it, like this mic here that I'm not using. And I tell you, figure out what's the behavior of this box, because I want you to come up with a circuit design that does the same thing as this box. And then I can give you some more challenges and say, I wanted to use less power, for example. Or I could tell you I want it to be smaller. Or I could tell you I want it to be flexible and integrated with my clothing so it doesn't look like this and it's not heavy on my pocket, right? Several ways of redesigning electronics. Okay, so I said the first thing that you can do in this task is to take the leads that come out of this and measure the IV characteristic, right? And see what's the behavior that you're getting from the box in the first place. So this, then, if it's a linear response, which in this class we will assume that is always linear, if it's a linear response, then you can model it as a very simple circuit that would involve either a voltage source and a resistor, or a current source and a resistor. And these two circuits here on your notes, there's a lot of talking and explanation about it, are called the Thevenin and the Norton equivalent. Okay, so two tools. One is when you are in the lab and you want to measure something to figure out, then you can just connect these leads, apply voltage, measure the current, or apply current, measure the voltage, right? So if I sweep the voltage from 0 to 3 volts, perhaps, then I will measure the current and make my plot, and then I know the behavior. Or I take a current source, attach a current source to it, provide a current to the circuit, a current that I know, or I can sweep the current, and then I measure the voltage and see how the voltage is changing with the current change. And that I get experimentally the IV curve. Okay, here in class, that's if you have a job that is related to hands-on jobs, right, in the lab. When I worked at Xerox, I worked in the lab. So I would always measure things, and I would build things and design things from the building perspective. But here, when we are doing design on paper, we are going to use this methodology differently, because we are going to look at the circuit, treat the circuit as if it was a box, and find a model that will provide us an IV characteristic that is equivalent to the Norton and the Thevenin equivalent. And then I finished the class when you guys are all ready to go and start packing stuff by saying that there were two rules here to get to this. And the first step in this methodology was to find V-Thevenin. And what is V-Thevenin? V-Thevenin is here when current is 0. So I said, experimentally, to find V-Thevenin, you connect an open circuit and then you measure the voltage out, right? So if I came here, took off with a multimeter, connected here in my open circuit and measured the voltage, I would be finding the V-Thevenin, which is the equivalent voltage for this circuit. Then, second step in this methodology is to find R-Thevenin, the equivalent resistance of this circuit. And to find that, we need to find the slope, because we know that the inverse of the slope is the inverse, the slope is the inverse of resistance. And we find that slope by zeroing out the independent source. What does that mean? That means I come here, in this box there is a battery, right? I assume there is a battery. Maybe there is not a battery, but I assume there is a battery here. That's our voltage source. How do I zero out a voltage source? I open this box, take the voltage, take the battery out, then I have zero voltage source, right? Then I come here and measure the resistance. That gives me our Thevenin. Sounds simple, right? So first, I connect a multimeter, a voltmeter, measure the voltage. I find V Thevenin. Take any power source that I have here and measure resistance. Then I know V, I know R, I can plot that, right? I know those 2 points. Okay, that was the methodology that I gave you. Now, today in class, we are going to apply this by to do circuit analysis. Do you have a question still?
Yeah, actually I was gonna ask, sorry, when we apply a voltmeter to the Thevenin, since a voltmeter functions kind of like an open circuit, why is there like current flowing through that circuit?
Why? What do you mean by current flowing through that circuit?
Like the Thevenin is an open circuit, right? You have the volt source, the resistor, and then two.
V Thevenin. You apply an open circuit, which is the voltmeter behaves as an open circuit. So that's what we're saying there. Find V Thevenin. So you connect there to measure the voltage. What is the current in an open circuit? Zero.
Oh, I see. Okay, got it.
Yeah?
Thank you. Yeah.
Great. Okay. Thanks for asking questions. It's always good, and this, feel free to ask questions. It's a new concept. Okay. Excellent. So today we are going to apply this in a different methodology. So let me just, for circuit analysis, which you can do in homework and midterms and in design, in paper, before you go and build something. Okay? So what I was saying to you so far was, for both, for the Norton or the Thevenin equivalent, you will get a circuit, which is a box, which I used here the microphone as a box, with zeroed source. When I say zeroed source, I mean zero voltage source or zeroed current source. Means I'm not applying any source of energy to move electrons anywhere. Then externally we can come here and connect these two open leads that we have here in this box of electronics, right? We connect these two open leads, and we could add, let me make it bigger. We could add a voltage source to it externally in the lab, right? We pick up a voltage source and we connect here our voltage source, which I'm going to call V test, because that's the test we are doing in the lab. So I pick up this circuit, I apply a voltage to it, a voltage that I know, a knob that we can turn and go from 0 and increase for as much as we want. And we know that then there will be a current that is going to be provided, which I'm going to call I test. There's nothing else. Okay. Once I know that I am applying a voltage and I can measure the current, I am sweeping that. And why am I doing that? Because then I know that our Thevenin, which was my equivalent resistor for that circuit, is going to be V test over I test. Why? Because we said that the Thevenin is a circuit that has a voltage source and a resistor. So if I'm saying the voltage source now is 0, all I have is a resistor. Right? That's what we did in last class. We had here that the Thevenin was a resistor and a voltage source. If I say this is 0, I'm going to measure what I'm getting here. I took the batteries out, this is 0, I'm going to measure resistance. How do I measure resistance? By sweeping the voltage, measuring the current, then I find a slope, and I know that the inverse of that slope is my resistance, which is R Thevenin. Okay? I'm just repeating what I said before with some formality. Other method that you can use in the lab is, instead of connecting a voltage source to that unknown beast inside the black box, you can connect a current source. And this current source now is going to be your eye test, connected here outside on the leads of your unknown circuit. And we know that we could still come here in these two leads and measure the voltage across that, which would be, actually, instead of being V element, would be our V test. Yeah? And when we add a current source, instead of having a voltage source to do our test, that is the Norton equivalent. And what are we saying? We are saying that the current source is 0. So if what was powering this box was a current source, I took it out of the circuit, I zeroed it. So all I have left is a resistor, which is the R Norton. So in that, sorry, my iPad, okay, there we go. In that case, I know that since all it would be left is a resistor, now I can say that R Norton is going to be, again, V test over I test. Okay? So far, this is if I have given you a task in the lab. You know, okay, I can do this, and then later on I can come up with a design that will behave like the measured IV curve. Now let's flip it. Now I'll give you a circuit like this one. And then I tell you, I want you to now analyze this circuit such that you tell me what is the equivalent resistance of the circuit without measuring, okay? Just by looking at the circuit, and I ask you, what is the equivalence of this circuit? Why? Because I want to have a very simple understanding, a very simple model that would allow me to analyze this circuit with the Thevenin equivalent circuit, which would be, oh, I have a voltage source, and I have only one resistor, because I think everybody agrees that that circuit is very simple, where this one is V Thevenin, and this one is R Thevenin, and I want you to find out what is the equivalent resistance for that circuit that I drew there. Okay, same methodology applies. We'll do this together, okay? So the circuit that we are looking at, our black box now is this. What's inside this red dotted line? That's our black box, but I'm telling you what it is, and I want you to tell me what the output in the lab would be. Okay, inverse role here. So what's step 1? Well, step 1 was 0 sources, right? 0 all sources. in this circuit that I gave you, do we have source? Do we have a voltage source? Do we have a current source? No, we have two resistors. So what's V Thevenin in this case? 0 volts, yes. So great, we start easy. If I ask you what's the Thevenin equivalent for this circuit, you can look at this and say, ha, easy. There's no voltage source, so V Thevenin is equal 0. Okay, that's step 1. Sometimes this voltage is called open circuit voltage, okay? For example, when we study solar cells or when you study diodes, instead of just saying V Thevenin, it will be called open circuit voltage. It means it's the voltage when current is 0. Because we know that an open circuit is equivalent to current 0. Okay. Now, step 2. What's step 2? Step 2 in the methodology. It was find R Thevenin. Now comes questions. Now it requires some thinking. Step 2 is find R Thevenin, which is, it was my first question to you. What is the resistance that is equivalent or equivalent resistance for the circuit? Okay, how would you do this? On paper now. Do you have an answer? You would say that? Why? Yeah. Okay. To find R Thevenin, he said, I would say R Thevenin is equal to R1 plus R2. And I am sure many of you who had done circuits before would say the same. And then I ask why, and it's like, right? I'll show you why. And this is sometimes a rule that you know by heart, that, oh, this is connected in series, so the result is this. Okay. Doesn't have a question yet, Div, but it will come. You can sit there. Oh, okay, so you have an idea. Okay, go.
No, I just saw that you'll apply a current source and measure, then you can like find the corresponding voltage by putting a voltmeter. And then you can like measure the resistance by, because you have the voltage and the current.
Yeah, so what he said was, why don't you apply a current source? Because then you can do your analysis based on the current, since we know that the voltage is 0. That's what you said? Did I? Yeah? Okay, that's actually a good suggestion. Why? Because I can take this circuit that's very simple. Let me just rewrite here so we do separately. So I have R1 and R2. I want to make a circuit analysis for them. And then the suggestion that we got was, let me connect it in red here. A current source to close the circuit, because then we can measure voltage and see what happens. And if we know current, we know voltage, we can find R Thevenin. And that is the methodology, because we know that if we use the Thevenin equivalent, R Thevenin is going to be equal V test over I test. Thank you. Excellent suggestion. So this current that we are giving here, we are attaching to our circuit now on paper, right? So we can do analysis. What are we going to call? I test. Thank you. I test. Okay. Now, I test is a known in our case, right? We know how much that's going to be because we decided that we are going to put a current source there. Before we do all the analysis, I have a question for you. Why would we not, can we, apply a voltage source there instead of a current source? Could we apply a voltage source? And I heard, okay, let's do democratically. Put your hand up if you think it's okay also to apply a voltage source to do the analysis of this circuit. Okay, yeah. Put your hand up if you don't know. Okay, well, you'll know afterwards. The answer is, yeah, it's okay. If you put a voltage source there, what do we make that circuit be? A voltage divider, right? Because it's a voltage source with two resistors. A voltage divider then means that in order to have our Thevenin, we are going to have to solve for the voltages because the voltages are going to be divided, right? So it's a little bit more equations, let's say. But if we apply a current source, it makes it simple. And this is part of design that you're going to learn, right? Oh, if I didn't know that, everyone that had your hand up, if you didn't know and you apply voltage source, it would still be okay. You would just get more equations to get to the result that I want to show here. And of course, you don't know what I want to show, so I'm just asking to see how you guys would approach this. Okay, I'm going to go with the current source because the current source is going to be simpler. Why? Because if I look at this circuit, I only have one branch, right? Which means that the current that I apply here will just go around this loop, correct? So is it okay for me to tell you that the current going around this loop is the same everywhere? Yeah, so is it okay for me to say that there will be a current that I'm going to call I1 going through here, and there is a current going through here that is I2, and because of the way we set up this circuit, we can say that I1 is going to be equal to I2, which is equal to, I test? Yeah? Ideally, that would be okay. All right. I don't see any complaints. So let's see if that's true. But we can, if we know I test, then we can now solve for V. I'm going to choose another color just so you know that now I'm going to be looking at this circuit differently. Once we made the decision, I want to measure voltage across these 2 points here, which I'm going to say that this voltage is going to be V test. Right? I am taking these two leads here, and I'm measuring the voltage across here, V test. All good? Now I'm going to come with my multimeter to measure, if we were doing practice. Here, what we can do is to apply the voltage law, KVL. And we can now have a circuit that we are very familiar with, where we have here one branch or one node, and we have this other node that I want to measure the voltage across. We also have a third node there, but do I need to make in my analysis take into account that node between the resistors? No, because I'm only interested in measuring the voltage between these 2 points, the potential difference between those 2 points. Well, if I call this 0 and I make this node my reference, These are all decisions that you are making on paper, okay, when you are analyzing your circuit. And I call that node up there U1. Now, when I look at the difference, I say, okay, U1 minus 0, the difference in potential between those 2 points is my V test. Yeah? Okay, but to go from 0 to U1, I'm going uphill, right? So I have to have a potential, I have a potential drop in R2 and I have a potential drop in R1. So let's use our tools, and I'm going to label now the voltages. So V1, the voltage going through resistor 1, where do I put the positive? Positive polarity for voltage across resistor 1. On the top. Why on the top? Passive sign convention. Current is coming this way. So I'm going to say there is one voltage across here, V1. Same thing for resistor 2 because passive sign convention, right? V2. And it turns out that for us to go from potential node 0 to U1, we are going from V2 to V1, right? So I can say that V test is going to be equal V1 plus V2, or V2 plus V1. Yes? Ask now before I continue. Is it clear? It's like going from reference from the bottom of the mountain to the top, taking 2 lifts. Yes?
So if we don't know what the thing inside the circuit box is, how do we know what V1 and V2 are?
Oh, we don't know when we are in the lab, right? So everything that I told you before we got here is what we are doing in the lab. Now here is, I give you this circuit, I tell you what's inside the box. And I ask you to make a model or analyze that circuit to give me the R Thevenin. Okay, so both sides, paperwork versus lab work. Okay, great question. Okay, now, do we know what V1 is? What's V1? Element definition. What element is element 1? Resistor. So do we know what V1 is? Thank you. It's resistance times current. And what's the current? I test. So it's R1 times I test. What's V2? Thank you. R2 times I test. Let me move this so I have more space. Okay. While I clean up, you can take a look and see if there is anything that you're not understanding, and please you ask questions. Okay. Now, the relationship that I'm looking for, the result that I'm looking for is R Thevenin, right? That was the task we had here at the beginning. I told you, tell me what's the equivalent resistance of this circuit. So what I want is to find a relationship such that I have V test over I test. Well, here I have V test, here I have I test and I test. So I can just isolate I. And now we are going to have V test equals R1 plus R2 times I test, which means that V test over I test equal R1 plus R2. formula that you had, you know, memorized, that you knew from the beginning. That's why. It's equivalence. Okay. This is when Mickey would say, okay, QED, which you know it's a radio station. Okay. Very good one when you want to hear serious stuff. Okay. So, what's your answer? The answer means that I could draw this circuit as just one resistor, which would be R Thevenin, and this R Thevenin is equal to R1 plus R2. And that's the definition of two resistance in series. When you know that when you connect in series, the current is the same. Means the current is the same. Okay. Clarifying questions? We'll do another example. Please, Div, run. Are you enjoying? You have such a nice smile, like, nice. You are? Great.
So if
It's
you
nice to
used
see. Okay.
sorry.
Go ahead.
If you used a voltage source instead of a current source, then would you arrive at the same final formula? For
You would. You would. You would just have more equations to solve, because then you would have to, you know, the voltage divider, then you would write the two voltages, and yeah, but you would arrive at the same. It's just, I use the current source because it would make things simpler. And why it makes things simpler? Because we already know some circuits that give us this intuition to say, oh, I would apply that. But if you follow the methodology that I'm teaching here, you don't make mistakes. Okay? Second example. See if you can figure out what you would do here. I give you two circuits again. And I say, okay, two resistors, but now the two resistors are connected differently than before. And I ask you, what is the equivalent resistance, R Thevenin, for this circuit? So, what would be your methodology? How would you do that? First step in that methodology is zero your sources, your power sources. Well, do we have a power source in this circuit? No. So that means that when we are trying to get to a circuit that has that has a voltage source and a resistor, where here is V Thevenin and here is R Thevenin, we already know that in our case, for this circuit, V Thevenin is equal to 0. Why? How do we know? There is nothing there, right? I'm telling you what the circuit is, and there's no voltage source there. So V Thevenin equals 0. Second is find the slope. Find the slope. How do you find the slope? You only find the slope when you have that R Thevenin is equal V test over I test. So now you either solve for voltage or for current. So take a good look at this, the way I connected these resistors. Have 30 seconds to discuss and tell me, would you connect a voltage source here or a current source? Discuss. 10 seconds. What would you connect? V-test or I-test? V-test. Why? Why? I'm hearing here. Yes, shout. Because the voltage is the same in those nodes, right? Which circuit is this? The interesting circuit. The surprising circuit, right? You have a question?
Yeah, I was wondering why are we doing all of this in terms of Thevenin and not Norton?
Oh, because it's essentially the same.
Okay.
You know, we started doing, I'll tell you why we do everything in Thevenin. Because the first time that Mickey and I taught this class was during the pandemic. And we taught it on Zoom. And every time I said the Thevenin equivalent, the caption said the feminine equivalent. So it became the feminine equivalent. and now I do everything with the Thevenin equivalent. But if you do the Norton, it just means, Norton means you are doing your analysis for current, while the Thevenin is where you do your analysis to voltage. But the circuit is the same, right? It's a resistor and a power source. So if you have a current as a power source, that resistor is R Norton. If you have a voltage as a power source, the resistor, the equivalent resistor is R Thevenin. Excellent question. In the notes, it explains all that. Thank you. Okay, so let's do it. What we are going to do is we are going to connect then, per your suggestion, we are going to connect a voltage source here to our open leads. Now we are going to provide power to this circuit, and we are going to provide power that we know, and we are going to call V-test. Okay. And now we know that there will be current, right? Because now it's not open circuit anymore. We close the loop. Now there will be current. And what we want to do is to measure the voltage across these leads here, which are our connections in our circuit, which will be V-test. Okay. What else do we know? We know that because of this voltage, there will be a current that I'll call I-test. There will be a current going here that I'm going to call I2. And there is a current going here that I'm going to call I1, because resistor 1 and resistor 2. Yeah? So far, so good? Please, go ahead.
Wouldn't passive sign convention dictate that I-test should go the other way?
Thank you. Thank you for that question. He said, wouldn't a passive sign convention dictate that the current had to go another way? Yeah, perhaps. Could I do this way just because I want to? Yes. Why? I'll tell you why. Now it's when I confuse everybody, but thank you. Okay, why? Because V-test here that I'm going to, let me put the laser here. This V-test that I'm going to measure is not, I'm not measuring this, right? I'm measuring what is in the open circuit here. So if I put the current this way in my elements, which are what is there in my circuit, that's why I put the current here, because I'm going to measure V across. Okay, let's say I want to be super precise and not do that. You get the same result, right? Because then that means that your currents will be the opposite and your signs will be negative, and it's okay. Because it's external to my circuit. It's not part of my circuit. Okay. If I had, let me continue answering your question. If I wanted to measure the voltage across the resistor, then I would have to say, okay, this is V2, passive sign convention. This is V1. Yeah? But what I want to do is to measure the potential. And I want to measure the potential between these 2 points. And I know that the potential between these 2 points is going to be equal to the potential between these 2 points, which is going to be equal to the potential between these 2 points. Because we already have done that analysis. Yeah? Okay. But I can ask you one question. What's I test? I1 plus I2. How do you know? I didn't teach you parallel. KCL, exactly. Thank you. So if you apply KCL to what? This point? Is that what you applied? Which is the node that you applied? So I'm going to choose a node. Okay. Pink, right, this one. Let's apply KCL to that. What does KCL say? KCL says that current coming into the node, I test, is equal current going out of the node, I1 plus I2. Very good. Excellent. Now, do we know how to, what's I1? No? What's your element 1? Resistor 1. Yeah. So what's I1? It's a, okay, element 1 is a resistor, which means that you can express current as a function of voltage and resistance. Very good. So what's I1? Very good. So I1 is going to be V test over R1, and I2 is going to be V test over R2, resistor definition. Okay, what we are after here is an expression of V over I so that we find the equivalent resistor. So let's just rewrite this equation where we can get to that. So if I know that I have I test equals I1 plus I2, which is V test over R1 plus V test over R2. Now we can rewrite this because we want to isolate, right, V test. So that would be I test equals to V test, times 1 over R1 plus R2. Okay, so what do we want? We want V over I. So we have to invert things, rewrite things, and when we do that, what are we going to get? V test over I test equals R1 times R2 over R1 plus R2. Now, in mathematics, this is an operator. What is this operator called? It's called parallel operator. That's why we say connection in parallel. You have to memorize this. Okay, let me just write here the conclusion. Parallel operator. Operator. Okay, very important. What does that mean? That means that the grand result here is that R Thevenin there, the initial circuit that I gave you could be expressed as only one resistor, as long as that resistor that we called R Thevenin would be equal to the parallel operator, which is R1 times R2 over the sum of them. Okay. Good? Makes sense?
Anna, we have a question.
Oh, questions. Okay.
So for the second line, after you do I test equal to V test, why do you put is there a reason why 1 over entire fraction R1 plus R2 becomes R1 R2
Yeah,
times
let me go back.
R1 over R2?
I will do like I did on the notes. All I did was you would have something like V test multiplying 1 over R1 plus R1 over R2. Thank you. Better? Yeah. Okay, questions about the methodology? You don't have a question anymore? It was that? Okay. Any other questions? No? Okay. Now I have a question for you. Oh, the question is there. What happens? What would you do if you had more than one power source? Special. So I tell you, I give you this circuit, 2 resistors, 2 power sources, you are familiar with these elements, and I say, what's the voltage V out that you are going to measure in those terminals there that are already marked for you? What would be V out? How would you solve this? With the tools that you have been given so far by me and by Mickey. How would you solve? Think, talk. Now, there are 2 power sources. What is the suggestion?
We thought you could zero one of the voltage sources and then do the analysis for the other side, and then do the same thing and zero the other one and do the voltage for the remaining side. And then
Okay, so that's a good suggestion. The suggestion is 0, 1 voltage source, and then solve for the one that is not 0, then 0 the first one, and solve for the second one. But what would be the result? What would be the result? Would it be the result from the analysis at the with first source or second source? What would be V out? Yes. You would zero both of them and find the equivalent resistor. At Thevenin, yeah. The V Thevenin. Okay. What would happen in that situation? Then you would have 2 voltages. Oh, you would, okay. Then you would have only the resistor with no voltage. you still at some point need to turn on the voltages, right? Mm-hmm.
I would apply Kirchhoff's voltage law around the outside loop, and then you would have like one of the voltage sources canceling out the other one, like going against it.
Oh, I see. But would they cancel out each other?
I assume so.
But what if one was 100 and the other one was 65?
I would intuitively think that like the 100 one would like the 65 one would push.
Okay, okay. So he's saying it would push, it would be, are you saying it would be a combination between the two?
Yes.
Yeah. So we're looking at linear circuits, right? So when you were doing module 1, you learned one of the conditions for linearity. What's the condition? That when you look at a system, you want to answer, Div.
I was thinking that like you could consider each voltage source like separately and then add up all the results.
Exactly. This is the condition for linearity, right? Because in linearity, you said if you have a system with two signals, you can push both signals at once and look at the result, or you can push one first, then push the second, and then you combine. The combined part is called? When you combine them?
Superposition.
Superposition, right. So, and I believe you were a subject here, right? When we passed one signal, and then we passed the other signal, and then you can either look at them together, or later you can do superposition and combine the results. Very good. So you have all of this in your pocket, okay? Don't forget what you learned before. It's all accumulating. Okay, let's do that then. Let's do this analysis following this methodology. First, I zero one source, then I zero the other source, find the results for both, combine, superposition, then I have the result for this circuit that might be complicated. And you might add or you might subtract, right? What you said was, the intuition was right. You said, oh, they'll cancel each other. They might, but they might sum each other. And as it turns out, this circuit that I have here for you is called voltage summer. They will be summing each other. Okay, at the very end. Let's do it. First step. Okay, let me do some naming here. This is important before you start doing your analysis, right? Think about what was asked of you. What I asked was, what's V out? V out is the voltage across these 2 points in your circuit, right? So what you want to know is the difference in potential between these two nodes. The rest we are going to treat separately. So I will mark this node, let me mark it for consistency here with my coloring. And then separate node, different color. Okay, all my nodes. Now, what I'm going to be doing is analysis between these two nodes. I'm going to make this one reference, I'll make this one U1. Sounds good? Why? Because then at the very beginning, before I scratch my head too much, I can say that U1 minus 0 equals V out. And V out is what I'm searching for. Everyone follows me up to here? Ask if you don't. Yeah? Okay. Great. Okay, first step. First step. I'll write it down. You have on your notes, but I'll write here. Bear with me. Compute. Meanwhile, while I'm writing, you write too. Write the circuit, how the circuit would look like if you zeroed one source, if you zeroed V2. So I'll say our first step was going to be compute a response. To V1, VS1, which means, in other words, we are going to set V2 to 0. How would it look like? Well, I'm keeping V1, so in my circuit diagram, I'm going to draw V1 here. And then I have resistor 1. And then I have resistor 2. And then here I didn't have anything. In the middle here is where I'm going to measure my voltage. Okay, and when I set V2 to 0, what element am I going to draw in my diagram instead of V2? A wire. Why? Because of equivalence. Because voltage source equals 0 is equivalent to a wire. Why? Because when we looked in last class, we looked at the IV curve for a voltage source. How does it look like? An IV curve for a voltage source looks like this, where this is Vs. But if I say Vs equals 0, then it will look like this. And this is a wire. Yeah? So when Vs equals 0, the equivalent element for the voltage source is a wire. You can start speaking very fancy now. Okay, now that we have this circuit, I tell you, what's V out? What's V out? You're doing homework, right? What's V out? Which circuit is this? What's the equivalent circuit here? Voltage divider. What's V out? V out is the voltage right there between the two resistors. Therefore, you can say with all your confidence that V out is equal R2 over R1 plus R2 times V1. Isn't it nice? So nice to have operators, to know operators. Life becomes easier. Okay, well, let's hide Leo here for a while. Okay, now second step. So what did we do? We found the first branch. Second step will be what? Compute a response for V2. Please ask your question.
I was just hoping to clarify why R2 is on the top. I guess I just want to understand or clarify which one goes on the top.
Okay.
Myself.
In this case, R2 is on the bottom, right? It's just you just flip the circuit. Like make the wire a little bit longer, and then you're going to have R1 here, R2 here. What I'm saying is, if you have voltage source here, and then you have the wire a bit longer, and then you have R1 and R2. R2 is on the bottom. Yeah? Am I right, or did I make a mistake? Okay. Thank you. You can say you made a mistake, you know? I make mistakes often. Yes?
For this voltage divider, if V1, the signs was switched and bottom was positive and up was negative, would V out be flipped again? R1 over R1 plus R2?
We are going to do the next one. Hold tight. Okay, next. We are going to compute a response to V2. Tell me, what does your circuit look like and what's V out when you compute a response to V2? Okay, so I'm going to say V1 is 0. If V1 is 0, instead of drawing V1, what am I going to draw? A wire. Right? Where I had V1, I'm going to draw a wire. Actually, I'm going to draw the wire last. Let me just write the circuit without V1. It would be R1, then R2, R1, then R2, then here I have V2, and down here I have my 0 node, and now on the other side where I had V1, I'm going to put a wire here to close the circuit. Okay, now what's V out? There you go. That answered your question. Became clear? Okay, what's V out? R1 over R1 plus R2 times V2. Very good. Thank you. It's a voltage divider, but now the resistor that is in the bottom is different. Very good. R1 plus R2 times V2. Huh? Okay, but what's total V out? So if we call this was V out 1 for when we had voltage source 1, this was V out when we had voltage source 2, that means that our V out total, terrible, total, would be R2 over R1 plus R2 times V1 plus R1 over R1 plus R2 times V2, the sum. Now this is amazing because this, don't erase my thing. Okay, this fraction here and the second fraction there, we control, right? These are resistors that we can now go to the lab. We can pick resistors such that at the end, we are going to be adding the voltage source. So if you put one voltage source of 1.5, the other voltage source of 1.5, the total V out, the equivalent, the V Thevenin, now is going to be 3 volts. And you can change that output by changing the ratio of your resistors. You could have one battery that is 1.5 with another battery that's 1.5, giving you an output that is different than 1.5. Cool? Gives you a lot of freedom in design. Yes, please.
I'm really sorry, I'm revisiting the earlier question. So when we talk about top and bottom, are we talking about the signage of the voltage source, meaning like the plus is?
Yeah.
Okay, so it's dependent on the direction of the voltage source, right?
Yeah.
Okay, thank you, sorry.
You have like to flip the diagram in your head. Yeah. Please. So that's why this is called the voltage summer. And you can do this analysis because I told you it was a linear system. You apply linearity and superposition, and you can use that solution. Go ahead. I was just letting Dave get to you.
I think you might have just answered it actually, but I was just wondering if there's any more like mathematical rigor to like why it's a sum instead of it just being kind of intuitive explanation.
No, it's a technique called superposition. It's basically here a practice problem for what you learn in linear algebra that was called superposition. But when Miki was talking about it, it was kind of abstract, right? It was like, if you have a system with two signals, you can pass both signals at once and look at them, or you can pass the first one, and then pass the second one, and then pass the third one, and then sum them. And here is a practical example of that. It's true because we're working with linear systems. Non-linear behavior, 16B. Yeah. Another question. So you will have to hop like an electron. Hop, 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 run. There we go.
Besides you telling us that it's linear, how do we know that it's linear?
How do you know that it's linear? I told you. Okay? I told you. I mean, in this class, we only look linear systems. We are going to start looking at capacitors, and capacitors are not necessarily linear all the time, but they get to a steady state, and we will look only at steady state. So here, you can assume that the circuit is linear unless I tell you that it's not. Okay? Excellent. Oh, good. So in your notes that I put, posted, I have here, I don't know why I'm getting this. I have here the formality for superposition, which you guys have done in module 1. And here how it would look like if you were to do the circuit analysis using the more formal linear algebra, right? So you would define your vector of unknowns and your stimulus, vector B. And then when you apply superposition, you would have an alpha multiplying I1, and then alpha multiplying another part of the current, and you would have the potential where there is a constant multiplying the current, and then you would have the sum of the terms, which we did in practice. Okay. More questions? So today was a powerful lecture for you, okay? Because you learn different tools, Thevenin, how to apply the Thevenin or the Norton equivalent, and superposition. So now the circuits that you're going to be getting on your homework are slightly more, not done, slightly more complicated. So now that you guys are going to become super experts on the resistive touch, because you know that you can model the resistive touch as an array of resistors. You know that when you connect a voltage source to these resistors here, to this array, you know that the potential difference between the nodes here, vertical and horizontal, will be the same. So you can really have a nice model for the resistive touch using the interesting circuit, and you're going to play with it in the lab. And I am going to start preparing you for the next touch lab that is going to be capacitive touch. And capacitive touch is more used by us because your phones, your iPads, your tablets, they're all capacitive touch screen. It would be nice to know how that works, right? So for that, to learn capacitive touch screen, I'm going to teach you one more element, which is the capacitor. And for the capacitor, you need to remember a little bit of the materials that I gave you at the beginning of the class, where I said, okay, Conductors, we have been using conductors for wires and for resistors. So here, conductors, we have been using 16A. And now we are going to start using insulators in 16A. And insulators, if you remember from that very first class, are materials where you need to provide a lot of energy for an electron to get to the conduction band, for an electron to be excited enough that it can contribute to current. And because that energy is so high, that means that that material is insulating electrons, and you should not see current going through that material. Okay? That's important because sometimes people say there is a current going through the capacitor, and that hurts my ears. Okay? So there is no current that can go through past a dielectric unless you see the black smoke, right? Okay. So what are capacitors? Capacitors are a storage, energy storage device. So you can store energy to be used later in a capacitor. So all your electronics have capacitors. Why? Because capacitors can give out that energy that is stored there. I think in your notes it says that a capacitor is like a bucket of energy. So the capacitors can be discharged. In other words, they can give that energy very fast for your circuits. So circuits that require fast power, they are powered locally by capacitors, which are later charged from a battery. What's the difference between a battery and a capacitor? They could both be looked as a power source. In the capacitor, a capacitor doesn't make energy, doesn't produce energy. It only stores energy. Stores energy between having an insulator in the middle. So you have two metals, two conductors, and those conductors you can use to charge a capacitor such that you would store energy there. And if you take that energy away and your capacitor is good, meaning doesn't have leakage, you're not losing current, then when you connect it again, you will get that energy. In a battery, you have a chemical reaction that happens between the anode and the cathode, and a battery, that chemical reaction makes energy, okay? That's the main difference. But capacitors and batteries have two electrodes, and here you can see that these two electrodes are typically made with conductors, and in between there is a dielectric material. They come in all sorts, shapes, and form. Very old capacitors, you would roll material, so you would roll a flexible metal film and a mylar, which is a polymer film that is very insulating. You would roll to make capacitors that can store a lot of energy. In your kit in the lab, you have tiny capacitors that look like this, but also store energy for your circuit. And I think you're going to apply capacitors mostly as filters, which you learn more in 16B. So next class, I'm going to teach you the physics of capacitors, and we are going to have our lab demo here, where we are going to show you how to charge, discharge, how not to charge and discharge capacitors. Okay? So have a great rest of your day. Be good citizens out there. Thank you. And I see you on Thursday.
I just have one question, sorry.
Go for it.
So, before the capacitor